In science fiction, there has always been the tendency to envision the first detection of an alien civilization as something very clear and clean-cut. But in reality, that's probably not how it will actually go, and will be far more ambiguous than perhaps we would like. This has already been the case in some sense. Every potential detection we've seen has been ambiguous, from the WOW signal to the new BLC-1 signal. They look technological and may fit the bill for a true alien radio signal, but unless they repeat and can be verified, they remain ambiguous and unproven forever. This is also the case for the first interstellar object Oumuamua, which my guest hypothesizes may have been technology of alien origin passing through the solar system. But this is not settled, with most of the scientific community skeptical, and the debate goes on. And it could be that we may never know, and Oumuamua remains an open mystery forever. But the discussion does need to be had, and not just for scientific reasons and answering the "are we alone" question. It's also a matter of this planet's security. That we even saw Oumuamua is because it passed not that distantly from Earth, and its existence suggests that there is a large population of strangely behaving objects passing through the solar system at any given time, literally in our own backyard. Because of that, all potential explanations should be seriously considered.
You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Professor Avi Loeb. Avi Loeb is the Frank B. Baird Junior Professor of Science at Harvard University, Chair of Harvard's Department of Astronomy, Founding Director of Harvard's Black Hole Initiative, and Director of the Institute for Theory and Computation within the Harvard-Smithsonian Center for Astrophysics. He also chairs the Advisory Committee for the Breakthrough Starshot Initiative, serves as the Science Theory Director for all initiatives of the Breakthrough Prize Foundation, as well as Chair of the Board on Physics and Astronomy of the National Academies. He is the author of 4 books and over 700 scientific papers. He is an elected Fellow of the American Academy of Arts and Sciences, the American Physical Society, and the International Academy of Astronautics. In 2012, Time selected Loeb as one of the 25 most influential people in space.
Avi Loeb, welcome back to the program.
Thanks for having me.
Avi, you have written a book that is sure to make waves, that covers not only the topic of Oumuamua and the very real possibility that it may have been a piece of artificial technology, alien technology, but also indictments of why we can't openly talk about things like alien trash in the solar system and the biases that are present in that. Now, where does this start, this bias within academia that it's never aliens and it's never going to be aliens?
Yeah, I find it rather unfortunate for a variety of reasons. First of all, I don't think it's more speculative than many of the things that are being done right now in theoretical physics. In particular, take for example, the study of dark matter. We don't know what most of the matter in the universe is, and there are several suggestions, and hundreds of millions of dollars were invested already in trying to build experiments that will search for those particles. We haven't found it yet, and nobody complains. It's part of the mainstream. In the case of dark matter, we don't know what we are looking for. It could be very different types of entities. It could be black holes that we can't see from the early universe. It could be elementary particles, or it could be that gravity is modified in a way that we haven't yet imagined. And all of these are viable. Now, in the case of the search for intelligent life elsewhere, because we apparently cannot find it here, if you open the morning newspaper, you're probably disappointed. In terms of that, we know that about half of all the sun-like stars have an Earth-sized planet in the habitable zone where it can sustain liquid water on its surface and have the chemistry of life as we know it. And that we know from the Kepler satellite data. It's just a paper that appeared a month ago. And if the Earth-Sun system is so common, and you roll the dice billions of times within the Milky Way galaxy alone, what's the chance that we are special and unique? I mean, it's quite likely that if you have the same conditions, you get similar outcomes. And we should search for it, that's all. Now, this is not speculative. Imagining that under similar circumstances, you get the same outcome should be mainstream. That makes no sense whatsoever for us to be skeptical about it, to put it outside the mainstream, to just search for microbial life, primitive life. Let me give you another context for this. There was an announcement of potentially a signature of life phosphine in the cloud deck of Venus. That was announced in September 2020. And shortly afterwards, the mainstream of the astronomy community suggested that this may not be a signature of life, even if it's there, and actually maybe it's not there. And I asked myself, the same mainstream community is trying to advocate for big missions to search for microbial life, the signatures of oxygen and methane in the atmospheres of exoplanets. And at the same time is shying away from any techno-signatures. Now, if we find oxygen in the atmosphere of another planet, would that be really evidence for life? If you doubt that phosphine is, then oxygen can be produced by many natural processes. And the only way for us to actually be sure that we found evidence for life is if we find, for example, CFCs. These are the molecules produced by coolants and refrigeration systems and industries on Earth that cannot be produced naturally. The CFCs that deplete the ozone layer. And if we find evidence for CFCs, these molecules, that would clearly indicate an industrial civilization and therefore life. And so to me, for the same cost of these missions, why not talk about CFCs rather than oxygen? I mean, it's not as if we have to invest more money. It's just being more open-minded and searching at the same time that we search for oxygen in the atmospheres of planets, search for industrial pollution. So the way I see it is that there is this narrow-mindedness and conservatism in the astronomy community that prevents the search for intelligent life from entering the mainstream. And you may ask yourself, how dare the astronomy community, how dare the scientists shy away from this question when the public is extremely excited about it and science is funded by the public? So if astronomers have the tools to answer this question, they have telescopes, they have funding for future experiments and telescopes, how dare they say, let's not do it, or let's look the other way when there is some evidence?
Now, it's interesting that you mentioned the Venus detection of phosphine gas in regards to CFCs and looking for CFCs as a technosignature. Now, not only could it be industrial pollution, but it's also a very, very, very good greenhouse gas, those gases, that group. And you could terraform a planet with them. So if you saw a very, very clear, obvious marker of CFCs in a planet that might not be inside the optimal habitable zone of the star that it's around, you've just found terraformers, and you have just found aliens doing something that we can only just dream of. And that's the beauty of a technosignature, is that if you find one, it isn't just answering the "are we alone" question, it's what are they doing? What is this?
Exactly. Exactly. I should emphasize that aside from the question of are we alone, to which I'm quite confident we will find an answer, no, we are not alone, because we're not special. We have to be a little bit more modest, more humble. My daughters, when they were young, they thought the world centers on them. And then as they went out to the street, they found other kids and they got a better perspective. And so we as a civilization behaving like that and arguing, oh yeah, maybe we're alone, is immature, and obviously the way to mature is to find evidence. And I should say that once we find evidence, which I'm quite confident and could happen in our lifetime, then the question is, are we the smartest kid on the block? And And if you read the morning newspaper, you realize we are probably not, because we keep investing a lot of effort in either killing each other, fighting with each other. We are not cooperating, and that's a sign of intelligence, that you work together and help each other. And instead, we are wasting a lot of resources, in fights among nations and so forth. And people die as a result and so forth. That's not a sign of intelligence. And so I believe, that we are probably not the smartest kid on the block based on the way we behave. We are not the sharpest cookies in the jar, and as they say, and we can learn from those other cookies in the jar. And perhaps we will learn an important lesson by looking at the sky. That's a learning experience. And I hope that by seeing, for example, how other civilizations were extinguished, perished on their host planet as a result of going into nuclear wars or destroying the climate or doing something inappropriate. By seeing evidence for that, we will learn a lesson to get our act together and behave better. I call that space archaeology. Just like we dig into the ground, we can dig into space and find evidence for dead civilizations, and that would teach us important lessons.
And we may have just sort of scratched that surface with Oumuamua. Now, your new book, Extraterrestrial, The First Sign of Intelligent Life Beyond Earth, when does it come out?
It comes out on January 26, 2021, and it will be published in more than 20 countries worldwide.
As I mentioned earlier, the book covers several bases, and one of these bases, of course, is the bias against, what would you say, free thinking, ultra thought, something like that within academia, especially in regards to alien civilizations.
Yeah, I would think that academia would learn from lessons of the past, and for example, Galileo, he said, no, it doesn't look like, I don't think that everything moves around the Earth. I mean, it's again this human-centric view that everything centers on us, that we are important, we are unique, we are at the center of things. And Galileo, it all started with the Copernican revolution. And Galileo said, I just look through my telescope and you will see that, it makes more sense that we are not at the center of the solar system, And the philosophers at the time said, no, we know the truth. We know the answer without looking through your telescope. He was put in house arrest, but the Earth continued to move around the sun. It didn't change anything. So my point is, we can be stubborn. We can shy away from anomalies. We can put people in house arrest. Will that change anything? What do we accomplish by that? That we remain ignorant. And what I'm surprised by is that the scientific community has this taboo on discussing these issues and shies away from anomalies. And, we have very good evidence that most of the discoveries in science came from anomalies, things that we haven't expected. It's a learning experience. We see things that we haven't thought about before. So why not be open-minded? Why bully anything that looks different? Why stick to old it just makes no sense to me.
What do you think causes this? Where does the disconnect? Because most scientists as children, they don't start out this way.
Right.
Where does the disconnect happen?
I think, unfortunately, I wrote, for example, an article in the Harvard Gazette encouraging, I was asked, what is the thing that you would like to change about the world? And I said, I would like my colleagues to behave more like kids. That's the thing I would like to change. Because kids are honest, straightforward, they experiment, they have ideas and then they check them and very often they fail, but they learn from this experience. There is nothing to be ashamed of. It's part of the learning experience. Einstein was wrong 3 times in the 1930s. He wrote 3 papers that are completely wrong. He thought the nature of quantum mechanics cannot be action at a distance. It makes no sense. He thought that black holes don't exist. He thought that gravitational waves don't exist. And then in 2015, we found gravitational waves as evidence for black holes. We have experiments that confirm quantum mechanics in a way that Einstein did not anticipate. But it's part of a learning experience. Even Einstein, the person that is regarded as the smartest of the past century, even he made mistakes, and it's nothing to be ashamed about, because we are learning new things about reality by having a dialogue with nature. The only way not to learn is to close yourself off. And you ask me, why are people doing that? The answer is simple. They are more interested in promoting their self-esteem, in promoting their image, in gaining awards, gaining status. And if you take risks, if you allow yourself to be wrong, then you might stumble here and there, and you are not optimizing your chances of getting an award or getting into a honorable society or being highly praised by your colleagues. And I claim that all of these rewards are nothing like the reward of understanding nature better. You know, who cares about whether another person thinks highly of me? I mean, that is irrelevant. Who cares about whether the philosopher at the time thought highly of Galileo? People remember Galileo, not these philosophers. Why? Because he said the right things. And so in retrospect, what matters is what reality, what nature is, rather than what people think it is. The number of likes on Twitter do not matter. So unfortunately, what happens in academia is people are driven by trying to promote their image, and therefore they are shying away from making mistakes. They also try to create echo chambers where whatever they advocated for early on in their career is being repeated by their students and postdocs, so that they get a bigger echo and have a higher chance of getting awards. As a result, those young people are very afraid of saying anything to the contrary, because then their prospects for getting jobs will not be great. Now, there is another layer that comes into the search for intelligent life, and that is the public is extremely interested. There is a whole literature on science fiction, and it feels as if you are degrading yourself if you are in the ivory tower of academia, if you were to talk about things that are otherwise the subject of discussion of people that do not have the expertise of being a physicist, a scientist, and so forth. And so, and it opens a lot of possibilities. And so, as a result, a lot of my colleagues prefer to maintain the image of being part of an elite. And, that is a self-inflicted wound, because then the public views academia as an elite. And I don't think that's appropriate, because I think the scientific inquiry, is just, science is a way of life. It's not really a job. If I have a leak in the faucet, or as I see something bad going in the pipe, then when I try to fix it, I operate just like a scientist. I try to figure out what the evidence is, what can I draw from that, and how can I fix the problem, And it's a way of life. Science is thinking about reality in a way that is based on evidence, trying to figure out how to act. And if you accept it as a way of life, then it's not an occupation of the elite. It's trying to figure out reality, and scientists should not be those that are elevated to a high social status. They should be every person, that has the evidence could conclude the same thing. And so I find this really unfortunate that there is this disconnect between the interest of the public in exploring this particular subject, for example, and the reaction of the scientific community, not only not to address this subject, but to bully and, say, ridicule anyone, that tries to address this subject. Because what happens then, the young people do not enter this research field. As a result, you don't have high quality scientists working on it. And then all these people that bully whoever works on this say, look, there is not much interesting stuff going on there. On the other hand, there is a lot of interesting stuff going on dark matter, on string theory. Now, we have no clue whether string theory is correct. It could be a complete pipe dream. For 50 years, they haven't made a prediction that was tested. We have no clue about supersymmetry. I mean, in fact, the test of supersymmetry indicated that at least the early versions of it are ruled out by the Large Hadron Collider. There is no evidence for the types of dark matter that were advocated for decades, for which people got awards. There is no evidence for all these speculative extra dimensions, all these speculative things. And yet they are part of the mainstream just because they are not accessible to the public. Extra dimensions involve sophisticated math. So, all these mathematical gymnastics still keeps the academia elevated relative to the public. Who cares about mathematical gymnastics? The question is, do extra dimensions exist? Let's check it experimentally. If there is no evidence for it, then this is much more speculative than the existence of intelligent life, for which we have evidence. We find it here on Earth, right? So if the conditions are replicated, why don't we search elsewhere where the conditions are replicated? So I find this situation right now as completely unhealthy and inappropriate, and I'm trying to correct it.
Now, it's one thing that you mentioned that is interesting. Einstein was wrong, but when Einstein was right, general relativity, there were still people that said he was wrong. As a matter of fact, there was an entire book with a bunch of signatures on it, all saying you're wrong, even though it was an obviously testable theory.
Actually, Einstein was asked about this book that was written about the theory of relativity, and the book had all these people contributing to it or signing on it, saying that his theory must be wrong. And he said, why do you need 30-some people to make the case? If they had a good argument, then, a single individual could have made the argument, and that's it. A kid could make the argument. You don't need authority of 30 people to make the case that the theory is wrong. Just, a good argument advocated by a kid could be sufficient. And so the mistake that people make is authority matters, and that was the case also in Galileo's days. Authority matters. Authority does not matter, and that's what Galileo said. It's even a single individual that has the correct, evidence and the correct argument could be telling the truth rather than the authority. I mean, we're not talking politics here. It's science. We're trying to figure out what reality is about. And the question is, who is telling the truth? And the only way to find out is by collecting evidence. And if you don't allow yourself to collect evidence, if you don't allow yourself to find wonderful things, you will never discover them.
This happens a lot because you also mention in the book about exoplanets and how the study of exoplanets was set back 40 years because of an incorrect consensus. Could you tell us about that?
Yeah, so Otto Struve, who was an astronomer, highly respectable, he wrote in 1952 a paper saying, perhaps we should search for a massive planet like Jupiter very close in to a star, because if it's close enough, then the star will move back and forth in a way that we can measure. And that would indicate that the planet exists around the star. At the time, people didn't know whether planets exist around stars. And so for 40 years, time allocation committees on major telescopes refused to give time, observing time, to search for such planets. Because the argument was, we know that Jupiter in the solar system is highly removed from the sun and gives it a very little tug back and forth, and it would be very difficult to detect that. And we understand why Jupiter is so far away. It has to do with water ice forming at some distance from the sun, and then Jupiter ended up with a core made of a rock, but then dressed up with hydrogen and helium, so we know where it formed. And all planetary systems should behave the same way because there is some underlying physics that we understand. And then about 40 years later, by chance, some astronomers were able to search for a hot Jupiter, a Jupiter that is close into a planet, to a star, and found evidence for it. And the Nobel Prize was awarded last year for that discovery of Michel Mayor and Didier Queloz. And the lesson of this is, you may argue, okay, science makes its discoveries anyway. In this case, it did make it. My point is, it's an inefficient process, and it was delayed by 40 years. And 40 years is a significant amount of time. Now, in this case, it happened. But imagine all these other cases where it didn't happen. I'm sure there are many cases where the mainstream community was arguing against even checking something, and it was never done as a result. And we missed an opportunity for a discovery. So for every case, when I find an ant in the kitchen, I get alarmed because one ant indicates that there must be many more that I haven't seen. And so when I see a case like that of hot Jupiters barely being discovered 40 years later, I know for sure that there are numerous cases where ideas were suppressed and as a result were missed opportunities. And, it's just a pity. It's just a pity that we are not, the scientific process is not as efficient because of prejudice. It's not as if the telescope time was not available. People used it to search for binary stars, for example, but not for a planet close to a star. Why? Why would we do something that is rather boring than allocate, let's say, even 10% of the telescope time for something that is risky? So my point is simple. Let's allocate a fraction of the resources for risky propositions because we never know what we might find. And the same is true about anomalies. If we see anomalies, we should not brush them under the carpet, under the rug of conservatism. We should not say, oh, no, we haven't seen anything. Forget about it. Nothing was business as usual. We should not do that. We should be honest rather than raise dust and claim that we don't see anything, which is very often the case. So the mainstream advocates often raise some dust and say, we don't know this, we don't know that, there is a lot of uncertainty, we don't see anything. Instead of raising dust and saying we don't see anything, just let the dust settle and admit when an anomaly is a real anomaly, and let's explore it. What's the big problem? Maybe there is something that we haven't expected.
You use a wonderful quote from Heraclitus of Ephesus in the book. If you do not expect the unexpected, you will not find it. Now, my question for you is, Oumuamua set aside, do you think it's possible that in the last 100 years of SETI and every other radio astronomy, everything, that we might have actually detected alien civilizations and missed them because of bias?
Quite possibly. I can give you an example. Gravitational lensing. That's the effect associated with the deflection of light by the force of gravity. In the Astrophysical Journal, which is the most prestigious journal in the United States that publishes papers in astrophysics, in the Astrophysical Journal, you can find papers dating back decades that showed images of clusters of galaxies where you can see those arcs that you expect from gravitational lensing of a background galaxy. So there is a source of light behind the cluster, and the cluster lenses the light by the force of gravity. And as a result, you get those arcs, which are distortions of the images, stretching of the images of the background galaxies that are being lensed. So if you look at the Astrophysical Journal, you find those images with the arcs in them. And nobody said anything about those arcs. People just, said, oh, maybe it's an artifact. I don't know what it is. This is not part of the paper. Let's move on. Business as usual. And then at the beginning of the 1980s, the subject of gravitational lensing got more popular. It was originally discussed by people like Einstein and Zwicky, many decades earlier, but it was not part of the mainstream, so people just dismissed it. And then at some point in the early 1980s, it became popular. And then people went back and said, oh yeah, you can actually get those arcs from gravitational lensing. Nowadays, people use those arcs to measure the mass inside of clusters of galaxies. And it's a well agreed upon procedure. It's part of the mainstream today. So you ask yourself, the evidence was there all along. Why didn't people interpret it correctly? And the answer is, it was not popular. If someone would have suggested, and actually people suggested that. Zwicky talked about gravitational lensing in clusters of, but people just ignored it, ignored him. He was not liked by many people. He talked about the dark matter. He was talking in a way that didn't appeal to people. Nowadays, he would get very few tweets. He would get actually bullying on Twitter. because he was not popular, Zwicky. But he advocated dark matter, he advocated gravitational lensing. So what? He was not popular, nobody paid attention to him. And then decades later, this subject became, both subjects, dark matter and gravitational lensing, became the highlights of astronomical research. So people say, oh yeah, Zwicky talked about it. But at the time, they dismissed him completely. And he was not considered, he was considered a wild card, so to speak. And what I'm trying to say is that the evidence could be there, and we are ignoring it because people simply say business as usual. People declare it publicly. Businesses forget about it. Just let's move on. It's easy to do that because if you try to deviate from that line, from the I would say the Pravda line, the official line of the party, if you are trying to say something different, you are risking future job opportunities, because those people that write Pravda, the newspaper that advocates the party's line, those people are the ones in selection committees. But then you think about it, we're talking about science, not about politics, right? So, and science makes progress by looking at evidence, and science is supposed to be based on independent thinking, but it's not. And that's unfortunate. And, I'm speaking to you as chair of the board on physics and astronomy of the National Academies, as a the longest serving chair of the astronomy department at Harvard, as a member of the President's Council of Advisors on Science and Technology, as the chair of the Breakthrough Starshot Initiative. I have a lot of as the director of the Black Hole Initiative and the director of the Institute for Theory and Computation. I have a lot of leadership roles, and I'm supposed to be part of the mainstream. I'm supposed to line up with whatever everyone says, but I refuse to do that because I still am genuinely interested in what nature is about. And I haven't changed much since I was a kid. I'm really curious about these things, and I care less about what other people say.
Now we have to take a break, but when we come back, we will get into Oumuamua, which may very possibly have been a piece, or is a piece, of alien technology, which you detail very succinctly in your book, Extraterrestrial, The First Sign of Intelligent Life Beyond Earth by Dr. Avi Loeb. We'll be back in a moment. And we're back with Dr. Avi Loeb. Now, Doctor, this book's main subject has been something that's been floating around and discussed within astrobiology for a long time, but since it was discovered anyway. But if you look outside of your book, it's an open question. Nobody seems to want to even address Oumuamua now. They seem happy to just let it sit there as having been something that we don't know, an anomaly, and it's gone. And we'll never know anything more about it. But I think that is unfair because a lot of data was taken on it, and that data points in a very strange direction. This was not a normal object. In fact, it was impossibly abnormal, you could say, I suppose. What is it about Oumuamua that sets it apart from anything else?
Right. Well, it's the experience is very similar to going on a beach and looking at seashells that were swept ashore, and usually they are beautiful. Each of them is different, and they were naturally produced. But every now and then, when you walk on a beach, you find the plastic bottle that was produced artificially. And when we have looked at the sky in the past, we saw mostly rocks, icy rocks in the case of comets. And when there is ice coating the surface, then it can sublimate and evaporate when the object gets close to the sun, and you see a cometary tail as a result. So we have seen comets, and we have seen just pure rocks, asteroids, from the solar system that were part of the debris made during the formation process of the planets and the sun. And then Oumuamua was the very first object that we discovered in the vicinity of the Earth that came from outside the solar system. So immediately astronomers conjectured that it must be either an asteroid or a comet, because that's what we have seen in the solar system. Sort of like a caveman, that works with rocks all his life, and suddenly sees a cell phone and thinks that it must be another rock. So it's completely natural, if your experience is with rocks, to think that Oumuamua was either a comet or an asteroid. The problem is that when we started to collect data, it looked like it has a very extreme shape, unlike all the rocks that we have seen before. It changed its brightness by a factor of 10 as it was tumbling around. And that indicates that the area that it covers on the sky changes by a factor of 10, because all we see is reflected sunlight. And the amount of sunlight tells us about the area projected on the sky. And imagine even a razor thin piece of paper. You never see it exactly edge on. So if the paper tumbles around and you see variations by a factor of 10 in the area that the paper projects, it means that indeed you have a very extreme geometry for the object. It's at least 10 times longer than it is wide, if not much more. That was the first indication that something is weird about this object. We have seen factors of 3 or so for solar system objects before. But then, in addition, this object exhibited a push away from the sun. And usually such a push can be provided by evaporation of ices on the surface of a rock. So, if it's a comet, what you would see is a cometary tail. But there was no cometary tail around this object. And the Spitzer Space Telescope looked very deeply and couldn't detect any heat coming from this object or any carbon-based molecules, either dust or carbon-based molecules, nothing of the type that we have seen in cometary tails before. So to a very high level of confidence, one can conclude that it doesn't have a tail that characterizes comets. So what pushed it then? And then it looked like this object started from a very special frame of reference. So this is the frame of reference that is associated with the galaxy, sort of the galactic parking lot. When you average over the motions of all the stars in the environment in our local environment, you get the so-called local standard of rest. And this object was at rest in that frame. Only 1 in 500 stars is so much at rest as this object, Oumuamua, was. We just bumped into it like a ship that is bumping against a buoy on the surface of an ocean. And the question is, why is it so rare? If this is the first object we encounter, why only 1 in 500 stars have this type of velocity, being at rest in the local frame of reference? It's sort of like a car parked in a public parking lot. Obviously, you cannot tell where this car came from. If it was moving from, you would see its trajectory coming from another garage. They would say, oh, that belongs to that person, perhaps. But this object was sort of in the local standard of rest, so we cannot tell which star it came from. And in fact, very few stars have those kinds of velocities. And then we didn't really expect to find an object like that, because a decade ago, I wrote a paper with colleagues, Ed Turner and Amaya Moore-Martin, where we showed that if you imagine other planetary systems being just like the solar system and ejecting rocks the way the solar system did, you wouldn't expect to discover this object. You need an abundance of objects that is 100 to 100 million times bigger than expected in order to get one of them detected, like Oumuamua was. So we didn't expect Pan-STARRS to find anything of that size, 100 meters or so, and yet we found it. So something is strange about its abundance, that you need much more stuff if you assume that it comes from a population of random objects that move on random trajectories. And then there was no heat detected from it, so then it means that it must be rather small, because otherwise we would detect the heat coming off it. We know the trajectory, we know what surface temperature it had when it passed close to the sun, yet we haven't seen the heat. It means that it's rather small, and it's quite shiny, at the upper end of the reflectance of objects that we find usually. And so it's a shiny, small object that is most likely actually flattened, a pancake-like geometry, because when you try to model the light curve, the 90% confidence level, Sergei Mashchenko, that wrote a paper about it in 2019, argued that it should be a flattened geometry, not a cigar shaped like was depicted in all these in the popular media. So it's a flattened object that has an extreme geometry that is very long compared to its width, and then it's shiny and relatively small. And so what is it, and what is the extra push that it received? And so we suggested in a paper with my postdoc Shmuel Bialy that perhaps it's a light sail that was pushed by sunlight. And if so, then it must be artificial, and therefore must have been produced by another civilization. And so that's what we published in a scientific paper in the Astrophysical Journal. And of course, people immediately responded within the scientific community with ridicule, saying, oh no, that cannot be the case, with no evidence. And there was even a Nature review paper saying it is natural, period. Now, they didn't really provide any good arguments. Why is it natural? And why all these anomalies that I described can be explained altogether in a natural way. Each of them is a very small likelihood. And when you multiply small probabilities one after another, you get that the chance of getting all of them is really small. So how can the mainstream argue business as usual? That to me is a puzzle. And they just made that statement for political reasons, just to say, this is it. And so that people will move their attention away from this object to some other things and not even consider the anomalies. Now, I should say that despite this claim, business as usual, by a group of people that wrote a review paper in Nature, there were some people in the mainstream that said, okay, well, let's forget about this claim. Let's try to understand the properties of Oumuamua and try to explain them in a natural way. So one suggestion was, oh, maybe it's a hydrogen iceberg, something that we have never seen before, an iceberg made just of hydrogen, so that you will not get a cometary tail of the type that we usually imagine. The problem with that, and we showed it in a paper with Thim Huang, we wrote a paper showing that over the journey of such an object, from a birth site, which let's say is a molecular cloud or a planetary system, over the journey, such an iceberg would be evaporated very quickly. And we have never seen a hydrogen iceberg before. So we argued it's unlikely to be the case because it wouldn't survive the journey. Then some other mainstream people suggested, oh, maybe it's a fragment from the disruption of a bigger object that passed close to a star. The problem with that is usually these fragments are elongated. Fragments caused by tidal disruption of an object are elongated. And most likely, Oumuamua was flattened. Moreover, the chance of passing close to a star is the chance is very small, and most of the time you don't pass close to a star, so there should be many more objects. And why would the first one come from a rare event where an object passed close to a star? That's surprising. And then there was another suggestion. Maybe it's a dust bunny, just of the type that you find in a household. It's so porous that it has a density 100 times less than the density of air. And then the sunlight can push on it. And then you would get the extra push from that. The problem with a dust bunny is that it's very fragile. And again, it probably wouldn't survive the journey. So this just illustrates to you that, people that took those anomalies seriously had to go a very large distance to explain them, with things that we have never seen before. We have never seen dust bunnies in space. We've never seen hydrogen icebergs in space. So trying to suggest those things indicates how difficult it is to explain the phenomena that we have seen. Yet the rest of the mainstream says, oh, business as usual, forget about it, it's a natural. Making such statements serve no good purpose. You have to address each anomaly and say how specifically, how do you get to explain it Is this a likely process? Does it produce enough objects at the abundance that is needed? And, the people that attempted to do that went into things that we have never seen before. Okay, that's legitimate. So why not consider also an artificial origin as one of those explanations? And then how can we make progress? Very simply, let's monitor the sky and find another object. So with Oumuamua, we realized that it's unusual only after it was receding away from us. And then it was too late because we couldn't really chase it. It was moving too fast for any rocket that we developed. But if instead of detecting it on the 19th of October 2017, we would have detected it in July 2017. And by the way, incidentally, that's the time when I visited Mount Haleakala in Hawaii, in Maui, where the Pan-STARRS observatory that discovered Oumuamua is. So if Oumuamua was discovered at the time that I was visiting that place, then we would see it coming towards us at that time, and we could have designed a mission to meet it halfway and take a photograph of it. But we discovered it only when it was receding away from us, and it was too late for us to chase it. So this was an unexpected visitor that came for dinner and then left out the front door into the dark night. And only then we realized, oh, it's very special, we should get more data about it. So instead, let's wait for the next visitor, because presumably it's not the only one. If it's the first one that looks so strange, then there must be more. The next one we find, let's get a photograph of it. Let's have a mission to chase it. But if you say business as usual, you would never even check others if they're unusual enough. I should say that there was a second interstellar object discovered called Borisov. It was discovered by Gennady Borisov, a Russian amateur astronomer that by chance found it. And that one looked just like a comet, a regular comet. So people came to me and said, oh, you see, this second object looks like a comet. So doesn't it convince you that Oumuamua was natural? And I said, look, when I met my wife on the first date, I thought that she's special. And the fact that I met a lot of people afterwards didn't change my opinion about my wife. It has nothing to do with it. She's still special. I'm married to her. So the fact that you find other objects that look natural doesn't mean that Oumuamua was natural. And if you find a plastic bottle on the beach and you find a lot of seashells that look natural around it, it doesn't mean that the plastic bottle is from the same origin as those seashells.
Now, let me ask you this. You mentioned shiny. Is that consistent with something like mylar, metal, or foil?
We don't know what it's consistent with because we didn't collect enough data about the reflectance as a function of wavelength of this object. So in principle, you could infer the composition if you have good enough data. But here is the problem. If your prejudice is that it's a rock, you wouldn't be even interested in collecting such data because you would say, okay, we have a lot of objects that we have seen before that appear reddish, sort of like this one. By the way, the outer solar system beyond the Kuiper belt, so the Kuiper belt is at 100 times the Earth-Sun separation, and that's roughly where the solar wind is stopped by the interstellar medium. And beyond that, there is the Oort cloud made of icy rocks left over, presumably from the formation event of the solar system. And those Oort cloud rocks, icy rocks, they are the most loosely bound to the sun. So if you imagine the solar system losing objects, most likely they would come from the Oort cloud. When there is a passing star, it could rip some of these objects apart from the solar system. But these objects are exposed to the same environment as interstellar objects that are unbound to the solar system, like Oumuamua was. We knew that it's unbound to the sun because it was moving too fast. And so it cannot be bound to the sun. And it went, in another direction, also unbound to the sun. And so these interstellar objects are exposed to the interstellar medium of the Milky Way galaxy. But the same is true for the Oort cloud objects because they are not protected by the solar wind. The solar wind is stopped much closer to the sun and at 100 times the Earth-Sun separation. The Oort cloud goes to 100,000 times the Earth-Sun separation. So there is a vast space of icy rocks bound to the sun that are exposed to the same environment as interstellar objects. And in principle, they should have the same surface damage as interstellar objects. So if we see an interstellar object that doesn't look like those Oort cloud objects, that would be a good indication that perhaps it's made of something different.
Which seems to be the case for Oumuamua. Now, the local standard of rest that you mentioned, as you said, that erases any data on where it came from. So if an alien civilization wanted to send a probe to our solar system, but keep their origin secret, that's exactly what they would do. They would just leave it in the middle of the road for the car to run over, right?
Yes, I mean they might not even intend us to get close to the center of the solar system. You can imagine a network of such objects being placed as relay stations for communication. You know, that there is no need to communicate by sending a signal across the galaxy, because then you need much more power. You can just have relay stations, either for communication or for navigation, sort of like signposts spaced throughout the interstellar medium. You can have those, and the natural system or frame of reference to put them in is the local standard of rest, where they are not associated with any individual star. They're sort of sitting there as signposts. Or there could be such objects that are intended to dive in to the habitable region of planetary systems, and maybe that's another possible interpretation. I don't know what the interpretation is, but the only way to find out is by collecting data on other anomalous objects. And so my point is really simple. I don't necessarily say that I know for sure that Oumuamua was artificially made, but I say it looks strange for the first object that we have found. It looks like a plastic bottle. Let's keep our eyes open for another one that may look strange, and then take a photograph of it, investigate it, get as much evidence as possible. Why have prejudice before we examine what reality is like?
It also seems strange that Oumuamua, not only for being such an unusual object and the first interstellar object we unequivocally saw, but also that it passed relatively close to Earth, almost as though let's tell ourselves a story that it was an alien probe. It did what an alien probe would do. It would see this interesting planet and pass relatively close by to it, right?
Right. Now, you might argue, okay, otherwise we wouldn't notice it because we rely on reflected sunlight that reflects off the surface of this object. And if it passes too far away, we wouldn't see it. But we will never know, of course, what the reason is that it passed so close to us. Yeah.
As Oumuamua left, it accelerated very famously, which got a lot of media attention. But the idea of something accelerating isn't unusual in and of itself. Comets can do that, outgassing and things like that, rocket effect. But this one did it very smoothly and without very much evidence of what exactly was going on there. What is the best way to characterize Oumuamua's exit from the solar system?
Yeah, so interestingly, the amount of push that it received, if you wanted to account for it by the evaporation of water ice, let's say, on the surface of a comet, you would need to evaporate about 10% of the entire mass of the comet in order to give it the push that was detected. So it's a substantial fraction of the mass of the object that needs to get evaporated. It's not a small amount, and we haven't seen any evidence. And so that's point number one. Then the other thing is that the push was very smooth with distance from the sun, and it changed, the extra force changed roughly as inversely with the distance squared. And if it was water ice, it doesn't follow an inverse square law, because there is a certain distance from the sun where water doesn't sublimate, doesn't evaporate anymore, and so suddenly you stop having this push. So there should be sort of a step, and there was no step like that in the evolution of the orbit of Oumuamua. It was a very smooth push, inversely scaling inversely with the distance squared from the sun. And that's what you expect from sunlight pushing on a light sail. I should say there was, in September 2020, there was another object discovered. This one was bound to the sun. Actually, it followed an orbit very similar to the orbit of the Earth, and it was given the name 2020 SO by the Minor Planet Center. So it was thought that maybe it's an asteroid or something, an object that was trapped in an orbit similar to the orbit of the Earth around the sun. And then this object exhibited a trajectory that showed evidence for a push by sunlight. And it didn't have a cometary tail. So the same qualities of Oumuamua. But then the astronomers integrated the trajectory back in time and found that it intercepted the Earth in 1966. And then they went to the history books and found that in 1966, there was a mission for a lunar lander that failed, and the rocket booster of that mission was launched into space. And so very likely this is the lost rocket booster. And it's a hollow, a relatively thin piece of metal, and that's why it exhibited the extra push from the sunlight. So here is an artificial object that we identified in the sky as having no cometary tail, as exhibiting a push from sunlight, and we concluded that it's artificially made. We made it. So to me, that's a confirmation of the fact that you can identify artificial objects by the way they behave. And it's again strange to me that nobody pointed out, oh, yes, this is a rocket booster from 1966 that we produced. It behaved in a way that looks similar to Oumuamua, even though it's bound to the sun, in the sense of showing the extra push from sunlight. And we know that it should have done so because it had a large surface to mass ratio. So it was a very thin structure that we produced. So doesn't that give you some confidence in the idea that we can identify objects based on the fact that they don't have a cometary tail and they show an extra push from sunlight? We can identify them as being artificial. So perhaps that argues that Oumuamua is artificial. Nobody made this point. And once again, business as usual.
Now, I am going to get one question for sure from the public, and I'm going to get it many times, so I must ask it. If Oumuamua is artificial technology and shows clear indications that it may be, should we take the UFO phenomenon more seriously and actually try to figure out once and for all, is it real or isn't it? What do you think?
Yes. So my view on UFOs, which are objects that are flying close to the surface of Earth, that are unidentified, and there are reports about such objects by pilots. There was a recent release of reports by pilots and other soldiers. And my view on these is that they are unlikely to be associated with alien civilizations. And the reason is simple. The evidence for UFOs was always on the borderline of being credible. It was never up to the scrutiny of scientific evidence. So it's always like based on fuzzy images, on some strange behavior. And my point is that our technologies evolved significantly over the past 50 years. So something that looked fuzzy 50 years ago with the present day cameras should be crisp, clear. We should be able to tell that they are out there, yet the evidence is always marginal. To me, this indicates that they're probably artifacts of the instruments that we use, because these would always exist. We would see something that looks strange just because our instruments for detecting those things misbehave. And that's my... So let me explain my premise. My point is, I don't think we are sufficiently interesting to distant advanced civilizations. I think most likely we are just like ants on a pavement, on a sidewalk. And when you are a pedestrian walking on a sidewalk, you don't pay special attention to every ant that is under your feet. These are primitive forms of life that are not noteworthy. They don't merit special privileges or attention. And I think that we are not special. I mean, it's sort of like those people that dream that a prince on a white horse will show up one day and pick them up. Like we as a civilization dream that maybe we're so important that they would come and visit us. But I don't think we are. I think we are a very common form of life, probably not the most intelligent. There are civilizations that are maybe 1 billion years more advanced than we are technologically, and their technologies would look like magic to us. And given that we are not special, unique, or we are still relatively primitive, there are many things like us throughout the Milky Way galaxy. So why pay special attention to us? I don't think they will come and visit us anytime soon, and they haven't done so in the past. So I'm quite skeptical that we merit an answer to Fermi's paradox. I think Fermi was showing arrogance in saying, where are they? Where is everybody? If you hold a party and nobody shows up, you can say, where is everybody? And obviously, the reason nobody showed up at your party is because you're not very interesting. Why would they show up? I mean, why would they care about you? You are assuming that you are so important that they must come and visit you if they exist out there. But they can have their own parties. They can be, in fact, if they are so advanced, they would isolate themselves in a cocoon. They will build their own habitat. I call it social distancing at a cosmic scale. It's now with the pandemic, we have our own social distancing. But you can imagine a very advanced civilization closing itself off, because it doesn't want to lower its quality of life. It has its own habitat. It enjoys everything it needs. So if you have such a cocoon that closes off an advanced civilization and they don't care about communicating with anyone else, the question is, will we ever find about them? And my answer is potentially yes, because they have to throw trash out. That's the second law of thermodynamics. Trash must be produced if they are using energy. And, it's sort of like investigative journalists that go into the trash cans of celebrities in Hollywood trying to find out gossip about their private life. We could examine the trash thrown out by those advanced civilizations and learn something about what goes on in their cocoons. But it's not at all clear that they would come after us and show their existence on Earth. And I think the evidence is clearly not up to the scrutiny of scientific evidence. There is a clear difference between Oumuamua, because there, telescopes that are used by the scientific community discovered those anomalies. It was not a matter of, a pilot just seeing something unusual.
And we have to take another break. And when we come back, we will get deeply into the budding field of astronomical archaeology, studying alien objects in space that may be passing through all the time or even landing on Earth in the form of meteorites. I am joined today by Dr. Avi Loeb, author of Extraterrestrial, the First Sign of Intelligent Life Beyond Earth. We'll be back in a moment. And we're back with Avi Loeb. Now, Dr. Breakthrough Starshot. Now we can get a laser-driven light sail to Proxima Centauri very quickly. It seems to me, couldn't we use the same technology to catch up to Oumuamua?
Yes, in principle we can, but we don't have the technology as of yet. We just started doing the research for the elements of this technology, namely how to create a powerful laser beam and how to create a light sail that is lightweight and yet sturdy, and also how to communicate with such a light sail. We only started to explore these technology frontiers over the past few years. So it will take us some time to reach the goal of building the infrastructure needed for such a scheme. But if we had it today, then of course we could have chased Oumuamua. By now it's a little too late, because as Oumuamua recedes from the sun, it gets fainter. And it gets fainter like inversely with the distance to the fourth power, because the amount of sunlight intercepted by the object scales as inversely with the distance squared. And then as it gets farther from us, we get another factor of 1 over distance squared for the flux that we receive. And so altogether, it gets dimmer and dimmer inversely with distance to the fourth power. And that's an extremely strong dependence, because it means that relative to the time when it was nearest to us, it's now at this time, it's 1 million times fainter than it was back then as a result of reflected sunlight. So if you ever send a mission to chase it, we don't know exactly where it went to the precision needed. You would need to equip this spaceship with a big enough telescope that would detect the reflected sunlight, a very faint object. That's almost impossible at this point in time. So we should maybe focus our attention on the next object that would look unusual, like Oumuamua, and meet it halfway when it's approaching us rather than chase it. And that would be a way of learning from a photograph much more about its origin.
Now, say we do see another Oumuamua, something with these weird characteristics. Can we do something so simple as fire a laser at it and try to accelerate it ourselves and characterize it that way?
Yeah, that's an excellent idea. That's one possibility, yes. It would tell us, whether indeed it responds to light like a light sail, whether indeed the origin of its push is the sunlight reflected off it, just like the wind reflects off the sail on a sailboat. So we can check whether that's indeed the origin of the extra push by shining on it rather than visiting it. I should say that in general, the light sail technology is a powerful way of exploring the Milky Way galaxy. You can imagine parking a lot of light sails around a star that is about to explode, a massive star that will go supernova, let's say in 1 million years. So you can put a lot of light sails around it, and then the explosion of the star will create so much light that it could push these light sails close to the speed of light. And they would surf on the light coming from the supernovae, just like surfers on the beaches of Hawaii, surfing on a giant wave, and in this case, a wave of light coming off from the explosion of a star, supernova. And so you can imagine a natural way of actually accelerating light sails based on a very bright source of light, like an exploding star, that could send off a lot of the light sails at a speed that we wish that we can accomplish with the Starshot initiative. And I should say that we are just at the beginning of developing our technologies. If you have a civilization that was around for 1,000 years, technologically speaking, or 1 million years, or 1 billion years, for them it would be trivial to get to this point.
This is the very beginning of astroarchaeology, or you could say another branch of astrogeology, because you get two things here. It is possible in principle that with interstellar objects passing through the solar system, that occasionally a sizable one might land on Earth as a meteorite. And it's possible that it could be an artificial one, a piece of alien technology landing on Earth. What would that look like? I mean, what would we just find a piece of titanium or something like that just wouldn't be possible in nature? What would we see?
So it really depends on the size of the object. The object needs to be larger than a person in order to survive in the atmosphere. Otherwise, it burns up as it goes through the atmosphere. It would look just like a meteor, and most meteors are not examined very closely when they pass through the atmosphere. Most meter-sized meteors are not studied in great detail, and some of these burn-ups may represent the burn-up of an artificial object. We haven't noticed it. Of course, if the object is big enough, then the core of the object can survive the passage through the atmosphere, and it would land. Most of the time, it would land at the bottom of the ocean. Every now and then, it would land on some surface of the Earth that we can examine. And of course, we could look for artificial objects. Most of the time, most of the objects in the solar system are not interstellar. They are associated with those asteroids or rocks that were left behind from the formation of the solar system. And most of the time, we would find natural sources like those seashells that I mentioned before. But perhaps every now and then, there might be an artificial object. And another place that is even better for us to search on is the moon, because the moon doesn't have an atmosphere, so nothing burns up. The moon is sort of like a museum that collects everything that comes its way. And there is not much geological activity. On Earth, if something hit the Earth more than 100 million years ago, then by now, geological activity would turn it around and it would be mixed with the inner layers of the Earth. But on the moon, there is no geological activity. And at best, it can be buried 10 meters deep, not much more than that, depending on the impact. And then in principle, we can look at those scars that the moon has from impacts of objects and search inside of them, inside those craters, search for perhaps a rare artificial object that was collected by the moon. Now, of course, these are not objects that can navigate or try to avoid impacts. These are objects that were sent out and then either became defunct, they're not operational anymore, or they're debris from objects that were left in space after a long time. And, it would be really interesting to examine the surface of the moon and Mars, I should say, for collections of such objects. Once again, this was not done, and we should be open-minded about it. It's sort of like a fishing net where you collect fish, and you might collect also plastic bottles in it. And of course, I should say that the solar system also has interstellar objects that were trapped by Jupiter and the Sun. They act as a fishing net. Every now and then, an interstellar object comes close enough to Jupiter so that it gets deflected and trapped inside the solar system. And we can find such objects. There are already some candidate objects. We wrote a paper about that with Amir Siraj, my student. And, in principle, you don't need to wait for an Oumuamua-like object to come through. You can go to these objects that look peculiar in the sense that their orbits are inclined relative to the orbits of the planets. And presumably they were trapped from interstellar space, and you can examine them. So one can design missions to objects that were trapped by the solar system.
And it pays to note here, too, that there is another aspect of this. Imagine the value of searching the moon or searching our own meteorite collections here on Earth, trying to identify which meteorites might be of interstellar origin, because all of a sudden you have a sample of an entirely separate planet-forming region, a solar nebula, and you can look at things like, what are the phosphorus concentrations in this meteorite? Because we know that within astrobiology, there's a problem called the phosphorus problem, and that it might be scarce in some areas, and that might preclude life. Well, we can look at these interstellar objects and say, how much phosphorus is in that, and see if that really holds true.
Yes. I should say so we went to a public data set of near-Earth objects, and including meteors, and looked at the data with my student Amir Siraj, and we did find one object whose orbit indicates that it was unbound to the sun. And so we pointed this out in a paper that we wrote a couple of years ago, saying perhaps this meteor that was identified in the catalog, perhaps it's the very first interstellar object, because it was discovered a couple of years before Oumuamua was discovered. And I was very disappointed by the response of the scientific community, because this meteor was discovered by sensors that are used for national security, for the defense of the country against the ballistic missiles, for example. And of course, this is classified information. So they put out just the data on this and other objects without giving official error bars, how uncertain are the measurements. But presumably these measurements are very accurate, and we actually received the information that they're quite accurate. But the referees of the paper said, oh, we don't trust these numbers that came from classified information. Therefore, the paper should not be published. And we tried to publish it, but we were blocked by the mainstream of people that work on meteors, because they didn't want this to be announced as the first interstellar meteor. They had a problem with that. And they basically argued that they don't trust the government, they don't trust the error bars, even though if you think about it, the measurements need to be extremely accurate, because if they were as uncertain as the referees were arguing, a ballistic missile that was supposed to hit New York City would hit Boston. You can't have sensors that are so inaccurate. And therefore, I have complete trust that these measurements were quite accurate and that this was most likely an interstellar meteor, but we were not allowed to publish this paper.
Any data on how big it might have been? Was it sort of just a dust grain, or could it have been something more substantial?
This was a substantial, meter-sized object that was definitely detected. The only question is whether its trajectory was measured precisely enough to be confident that it came from outside the solar system. And we checked with people behind the fence, the national security fence, and were told that the error budget would not allow it to be bound to the sun. But the referees, the reviewers of the paper, refused to publish it. And I was disappointed by that. And I should say, I was pointing this out in a Scientific American article that I'm disappointed by this response. And then the referees complained about my disappointment. Now, the referees know me by name. I don't know who they are. And it just shows you the imbalance in power. They can reject the paper based on just the assertion that they don't trust the error bars coming from, the national laboratories. I don't know who these referees are. I just point this out in a Scientific American essay, and they complain about me pointing this out. And, once again, it shows you how unhealthy the atmosphere, how acidic the atmosphere is to innovation.
And one must, yes, you may not trust the government's error bars, but a lot of them trust the government's money as far as funding and things go. And I have to admit, I am delighted to hear that the powers that be in national security can tell the difference easily between a nuclear weapon and a meteorite entering the Earth's atmosphere. At least that's reassuring. Now, this idea of collection points at Jupiter, this offers a pristine way to look at it. They don't have to pass through the atmosphere, these interstellar objects. They don't need to burn up or acquire fusion crusts. We can just go look at them. How difficult is it to get out to those collection points that Jupiter deposits material in? And I know that there are two candidates for burned out comets that may have originally been of interstellar origin. So what do we do to go out there and take a look at those?
Oh, it's just, it has to be defined as a space mission, just the way we visit Pluto or visit other objects in the solar system. It has to be defined as a goal to go near these objects and study them. And depending on the size of the mission, again, if we had the Starshot, we could have sent a spacecraft that is equipped just with a camera in the direction of these objects. So actually, it would be nice if future space missions would be cheaper because you send a very small payload, like a CubeSat or something smaller, that doesn't cost much, but you send it more frequently rather than have a decade-long mission design phase and so forth. You can send those cheap probes whenever you need it to multiple targets. It would be nice if we operated that way. And then we can look at targets of interest like those objects, and it wouldn't be too expensive. Right now, we don't have such a framework that allows us to send missions to distant objects at a relatively low cost. So it would be nice. I should say that currently there is another aspect to this entire question that we were discussing, and that is, what do we do with our own things here on Earth? I mean, currently all our eggs are in one basket. Everything that we hold precious to us is on Earth. And if something catastrophic happens on Earth, like, for example, a big rock hits the Earth and kills us, just like it killed the dinosaurs. The dinosaurs didn't have astronomy, they didn't have telescopes, they couldn't protect themselves. They just saw this giant rock coming in. It must have been a beautiful sight, coming in, and boom, and they die. We potentially could deflect dangerous rocks heading our way. But you can imagine other catastrophes, including the climate and so forth, within the next century or so. And then, if we perish, there will be nothing left. So it makes sense for us to spread our eggs, not to have them in one basket. And for that purpose, we can send missions to various places and put things that we care about in other locations. And, it's sort of like, I wrote a Scientific American article about it. It's sort of like Noah's Ark, the biblical story of Noah responding to the great flood, the risk from the great flood. He put animals, he built an ark. And by the way, this ark had dimensions very similar to Oumuamua, roughly 100 meters in length and 15 meters in width and so forth. So it's all spelled out. Anyway, he built an ark, and according to the legend, he put animals in it, and they survived the flood, and that's why life continued on Earth. So similar to Noah's Ark, you can imagine Noah's spaceship, creating a vehicle that preserves life beyond Earth, so that we don't have all our eggs in one basket. Now, you don't need to build a huge, gigantic spaceship for that, so that it can accommodate elephants, whales, birds, and so forth. You don't need to do what Noah did. Now, with modern science, you just need to know the DNA of everything that you hold precious, all these animals. You need to have an artificial intelligence computer system that stores all the DNA information. And you have to have the machinery, maybe a 3D printer, that is able to use raw materials that it finds on another planet in producing life, synthetic life. So we need to understand how to make synthetic life. We don't know it yet, but we might within the next decades understand how to do it. And then you don't need to carry these animals in a Noah spaceship. It could be just a CubeSat that has this computer and a 3D printer, and then it makes those animals, or at least the DNA associated with these animals, makes it on another planet. And that sounds much more attractive, because, for us to live in space, it will not be easy. It's a very hazardous environment. There are cosmic rays and so forth. So a much more elegant way is to send out a piece of technology that would reproduce what we care about on Earth elsewhere.
Flip that around. An alien civilization could do the same thing and send their genetic information out into the galaxy, which opens up the possibility of humanity at some point in the future finding alien genetic material that could be reconstituted into an alien, or 3D printed, as you said. Meaning that this is one way the human species, for better or worse, this could easily turn into a nightmare, but could actually see an alien.
Yeah, I should say that, although it's most likely that we came from a chemical soup on the surface of the Earth, that some chemicals came together and made life as we know it, and us as the end products of that process. It's also possible that we were planted on Earth, and that's called panspermia, from another place. And that doesn't solve the question of the origins of life. You still need to produce it somewhere else. But it helps in spreading it away, in many locations. If you manage to make it in one place, then you can plant the seeds in many other places. It's possible, that we originated in a laboratory somewhere, that our ancestry leads to a laboratory of another civilization, and finding our roots would be to trace them back to that laboratory. Now, I should say, if you go along this path, there are papers in the scientific literature talking about the possibility of producing a universe in the laboratory, something like the Big Bang. In principle, if you irritate the vacuum enough, the vacuum, a whole universe might pop out from the vacuum. And people discussed it in papers in the literature. We don't know exactly how to do it, but in principle, it's possible. And that would solve the origin of the Big Bang. What was there before the Big Bang? Because perhaps our umbilical cord leads to a laboratory of another civilization that created our universe at some point in time. So the Big Bang came out from an experiment in another laboratory. And, the nice thing about this idea is that our universe is now producing technological civilizations like ours. And at some point in the future, technological civilizations like ours may produce baby universes. So you can have the sequence of baby universes born out of existing universes, one after the other, that could perhaps explain why the universe had a beginning in time, according to the Big Bang theory. But even if you give up on this rather exotic idea, it's possible that life started in another laboratory, or that we would produce synthetic life. I would say within the coming decades, that's quite likely that we will be able to produce synthetic life in the laboratory.
This idea of creating universes in the laboratory, could you imprint a message? And I'm sort of hearkening to Roger Penrose here. Could you imprint a message some way onto that universe so that any inhabitants in it, say you fine-tuned it, say you looked at the anthropic principle and recreated it with your universe, could you leave a message for the people in there, should they ever arise?
I think that the most natural message is, if they are intelligent enough, they will figure out that in fact it's possible to make a universe in the laboratory, so they would make it themselves and then understand where their universe came from. So the message is that everything we see would point to the possibility that the Big Bang started from an artificial process. And currently we are lacking a theory of quantum gravity, a theory that unifies quantum mechanics and Einstein's gravity. And if we had such a theory, we could extrapolate beyond the Big Bang. We could have asked the question, is it possible for our universe to start out of nothing, out of the vacuum? We are not sophisticated enough yet to have a theory of quantum gravity that is trustworthy, that can make predictions. There are contenders for such a theory, like string theory or other quantum loop gravity and other theories. But at the moment, they haven't made the predictions that give us confidence that we are on the right track. But if at some point in the future, we'll be able to have a good working theory of quantum gravity, we might be able to figure out that the message is actually in the details of our universe, that we would figure out that such a universe can be created artificially, and then we will realize that our umbilical cord leads to another laboratory.
Now let's just take it. Let's take a sort of a thought experiment, a fun look at one weird aspect of the universe, the axis of evil problem, where the cosmic microwave background radiation appears to in some way correlate with the plane of the solar system. This should not be. Those two things are not related. Yet, observationally, it seems to be there. It's a little bit colder on, one hemisphere than the other in the CMB. So should we take that seriously and ask questions like, could that be a message, or could that be, did the creator sign the painting with that, or is it just very likely not to be the case?
Yeah, again, just like the UFO reports, this puts a lot of emphasis on us being in a special status, that we are important, therefore the message was intended for us to live in the solar system. Now, the Copernican principle, that's the principle that asserts that humans are not privileged observers in the universe, that we are not special. That's my starting point. Out of modesty, I call it cosmic modesty, we should not pretend that we are privileged observers. We are at a typical place, at a typical time, under typical circumstances in the universe. That's my working hypothesis. We find life on Earth. We find many other Earth-like planets that have similar conditions. Life like ours is there, quite likely. That's my working hypothesis. We are not privileged. We are not special. We have a solar system, that doesn't have anything to do with the microwave background that came from very early cosmic times. It just so happened that the solar system is oriented in a way that lines up with a cold spot. Who cares? So I would just say it's in my book, it's better to be modest and humble and not to pretend that we play a special role and things are really aimed to send us specifically a message, because we are not special. We are not unique. And our solar system is one out of so many others that are oriented in random directions. So why would the message be just for our solar system? So I suggest let's just be more humble and modest and assume that we're nothing special, and then explore the universe from that starting point. That seemed to work for cosmology, the study of the universe. We found, of course, the ancient Greeks, Aristotle said, oh, the Earth is at the center of the universe and everything else moves around it in spheres, And then Copernicus realized, no. And of course, we now have the idea that, the sun is one out of billions of other stars that look just like it. The Earth sun system is very common. Half of the sun-like stars have a planet like the Earth at the same distance. That nothing is special about us. And then we are all in the Milky Way galaxy, but there are billions, tens of billions of galaxies just like the Milky Way, many other places. And on very large scales, the universe is nearly uniform. So really, we are not at the center of anything. There are many things like what we see around us that exist elsewhere. We are not privileged. Okay, so we know that based on data for the physical universe. Yet we don't know it for the biological universe or for the technological universe. I suggest let's maintain the same principle. It worked for the physical universe. I think that we are probably not special in terms of biological creatures and technological creatures. So let's assume that we are not privileged. And then from this starting point, explore. If we were to believe that we are special, we might not explore. And that's what the mainstream is doing right now. And that's unfortunate.
And we have to take another break. I'm joined today by Avi Loeb, author of Extraterrestrial, the first sign of intelligent life beyond Earth. And when we come back, we will talk about a mysterious signal that was recently picked up coming from the direction of Proxima Centauri. Back in a moment. Now, Dr. Loeb, Project Starshot, the target is the nearest star to Earth, Proxima Centauri. Now, we have recently, SETI, and a SETI experiment has recently identified an interesting signal that appears to emanate from that area. Now, it's best to caveat before we go into this story was leaked, and the data is not out there for us all to, look at. But what does that change? Does that change the timetable of Starshot? Does it suddenly become the most important thing we could do is send microprobes to Proxima Centauri to see what this is?
Yes, so this signal that is called the Breakthrough Listen Candidate 1, BLC1, is the first signal that could not be ruled out as human-made on Earth, and looks suspicious coming from the direction of Proxima Centauri. But it could still be human-made. For example, there could be some oscillator that is producing emission at a very narrow frequency band of only a few hertz, centered on 980 megahertz, that is drifting slightly over time, that is artificially made by humans, and we just haven't identified it, and it's coming into the side lobes of the telescope. That could be the case. Perhaps it's the most likely interpretation. So we still have some work ahead to figure it out. And of course, one way is to use a different telescope in the southern hemisphere, a different radio telescope, and look at the direction of Proxima Centauri. Presumably, the environment will not pick up the same contamination from another location on Earth. And that would be a clean way, if the source repeats, a clean way of identifying that indeed it's coming from the sky, from Proxima Centauri. And moreover, we know that there is a habitable planet around the Proxima Centauri, an Earth-sized planet in the habitable zone where liquid water could allow the chemistry of life as we know it on the surface of the planet. It's called Proxima b, and it's 20 times closer to Proxima Centauri than the Earth is from the Sun. That's the distance at which the surface temperature of the planet is similar to that of Earth, simply because the star is a dwarf star. It's 12% of the mass of the Sun. It's much fainter, so you need to get closer to the furnace in order to maintain the same temperature. And obviously, the first thought that comes to mind is perhaps there is a civilization on Proxima b, and it transmits at this frequency that we detected. As soon as the news report came out on December 18th, 2020, I was able to immediately calculate the expected drift in the frequency of the signal as a result of the acceleration of Proxima b around its star. We know how much acceleration Proxima b has around Proxima Centauri because we infer the existence of Proxima b from the reflex motion of Proxima Centauri. So we see the star moving back and forth with a period of 11 days, and from that we infer that there is a planet pulling it back and forth with that period. And we see how much it moves back and forth, so we can infer how much the planet is accelerating back and forth. Just momentum conservation. So we know for sure how much acceleration the planet should exhibit over time. And given that acceleration, I calculated that the drift in the transmitter frequency would be much more than reported. I was not part of the discovery team. I was not aware of this discovery, but just thanks to the excellent reporting, both in The Guardian and later in Scientific American, I was able to infer that it cannot be a transmitter on the surface of Proxima b. And now the question is, it could still be a transmitter somewhere in that direction that has nothing to do with Proxima b. And one may wonder whether it's at all plausible for a radio signal to originate from the nearest star to us. So once again, I advocate the Copernican principle, which says that we are not privileged. We are not privileged observers. There is nothing special about the present time. Now, we know that on Earth, radio technology started about a century ago, and Earth existed 4.5 billion years before that. So we know that the window of time over which we were transmitting radio waves is a tiny fraction of the age of the Earth. And if we say, okay, we are not living at a special time, then the chance of another star emitting in radio waves near us is extremely small. And we quantify this argument in a paper with my student Amir Siraj, basically making the point that the Copernican principle implies that there is an extremely small probability that the nearest star to the sun is emitting in the radio right now so that we can pick up the signal. And I should say there is one caveat to this conclusion. The caveat is, unless technological advances here on Earth are correlated with those in Proxima Centauri. And you might say, why would they be correlated? Well, one interesting point about Proxima Centauri is that, stars come and go to the vicinity of the sun. And Proxima Centauri came to our vicinity at about the same time that Homo sapiens came to exist on Earth. So is it just a mere coincidence? Or was it perhaps the result of intelligent life being planted in both places at the same time? That's the only caveat that I can see, if there was a correlation between the two stars. Otherwise, I would argue it's very likely that this signal that was detected, BLC1, was made by humans here on Earth. And it's a one-time thing, just like the WOW signal that we haven't identified, but it must be something, in Australia near the Parkes telescope, some oscillator, cell phone, microwave oven, whatever, that produce the signal, then doesn't produce it anymore.
It's also worth noting that there is a sort of suspicious aspect of this signal. The frequency is very close to just a number, instead of so that seems to, and it's within the variation of what a bad oscillator might produce off from the target, transmission frequencies. So this sort of looks suspiciously like interference of some type.
Yeah, because the unit of hertz will not be common to us and another civilization. It's based on the definition of a second, and the definition, a second was defined by humans in a completely arbitrary way. You can measure time differently and define your unit of time differently than a second. So if it's an exact integer in hertz or in inverse seconds, for another civilization, it will not be an exact integer. And why would they produce radiation exactly at that frequency? That's a good point, yes.
It's interesting that you mentioned the idea of correlation. If intelligence may have been somehow kicked off on both star systems at about the same time, that's interesting. But that also requires some measure of co-development, doesn't it? Because we may have had radio 2,000 years ago if the Roman Empire had been a little bit different in its technological arc. So,
and the question is, how long will radio technology survive into the future? I mean, we are in the first, after the first century of its existence. If we live for 1,000 years, our culture exists for 1,000 years into the future, then maybe it's not so unlikely if you have a mismatch by 1,000 years. But you're right, that's a good point. I should say there are other ways to search for a technological civilization of Proxima b, and I wrote papers about it. One, Proxima b is 20 times closer to the star than we are from the sun, and as a result, it's expected to be tidally locked. It faces the star with the same side at all times as it orbits the star. So there is a permanent day side and a permanent night side. And by the way, my daughters argue that the sunset strip, which is a permanent sunset strip between the two sides, would have the highest real estate value because you can have vacations there on that planet if there is a civilization. But anyway, putting that aside, you can imagine that a technological civilization would try to put the photovoltaic cells on the permanent day side in order to produce electricity that would warm up the cold night side, permanent winter side, so to speak, and also illuminate it. And in that case, we could search for the reflectance of those photovoltaic cells. If they cover a significant fraction of the landscape of the planet, we would see some very unusual reflectance of the starlight from the surface of the planet, which we can examine with future telescopes. But in addition, we could find evidence for artificial illumination of the dark side. It will not be completely dark, and that would indicate that it perhaps is illuminated. It's easier to detect that if, for example, our hypothetical neighbors use LED lamps, light-emitting diodes that emit in a narrow band, because that is easier to detect with, for example, the James Webb Space Telescope that will be launched next year. So there are ways to infer the existence of technology on our nearest neighbor habitable planet and that are different from a radio signal.
So, in other words, if they have photovoltaic cells sitting on the surface of their planet essentially becomes shiny, just like Oumuamua.
Exactly, shiny, but also one feature of photovoltaic cells is they reflect much more at wavelengths that are longer than some threshold because they use light just like plants do. Plants have the red edge where they use up ultraviolet light, but they don't need to use red light. And so they reflect infrared light, and they're extremely bright in reflectance in the infrared. We don't have infrared eyes, but if we had, we would see plants glowing in infrared, even though they absorb a lot of the ultraviolet. And obviously, the infrared photons are considered as trash for the plants. I mean, they can't do photochemistry with them. So they just reflect them. They don't need them. They use the optical and ultraviolet photons. And photovoltaic cells have a similar feature, except the spectral edge is not the same as plants, as vegetation. And so we can look for a change, an abrupt change in the reflectance of the surface of Proxima b. And that would be indicative of photovoltaic cells.
All right, Doctor, we are out of time. Thanks once again for joining us yet again. And I hope we can do it again in the future.
Same here.
Thanks for listening. I am futurist and science fiction author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Gauthier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing. And be sure...
And that's enough of that.
YouTuber forever! Like, subscribe, and hit the bell!
Sell out.
What?